Hi everyone, I'm Chris Moran with HVAC Pro Blog, and this week I'm excited to share a video that I produced for my Patreon members 1 year ago. This week we're talking about Manual J and how seeing is believing. We're going to review heat transfer, material properties, R value, U value, temperature difference or delta T, and of course heat loss. So without further ado, here's the training. So we're going to talk a little bit about ACA Manual J. In order to do that, we're going to have to talk a little bit about some basics. When we really talk about a review of heat transfer, we're going to cover a little bit about material properties, okay? How that fits into R value, U value, and how temperature difference, how those impact heat loss, okay? So there is a little bit of elementary math here, but it builds up towards the seeing is believing and why you need to do a load calculation. I have a great example for you on how you have to actually see the insulation, let's say in an attic, in order to actually get the right math. And you'd be surprised how much it does impact your load, all right? So first thing, we're just gonna do a quick review. We're gonna talk about heat transfer, and the first piece is conduction. And if you know me, if you know training, I don't like to read slides, but when we're defining things like heat transfer, there's no real way around it. So I'm just gonna read this off. The flow of heat through a material or other material that it's in contact with, right? So you can see the ice is sitting on a table here and it's pulling heat because actually I shouldn't say it's pulling heat. It would only be doing that if it was colder. The ice is absorbing heat from the table and it's starting to melt. And that is actually happening with heat transfer through conduction because they're in contact. All right. This is very important to understand the difference between that and, of course, convection, right? Convection is the transfer of heat from a surface to a liquid or gas or vice versa, depending on which one's hotter. And that's typically done with air movement. So you can see in this example here, there's a fan in the background blowing warm air across a glass of ice. Obviously, that ice and water is starting to pick up heat as the air moves across it. So that's convection. And then, of course, the last one, which I'm sure if you've done anything in our trade, you know the last one's radiation, right? It's the transfer of energy through electromagnetic waves, right? So what we get from the sun, radiation. And just because it's cool outside doesn't mean there's not radiant heat coming on you, right? So if you're standing in the sun in the middle of winter in the Northeast, you can still feel warm and still get a sunburn if you're, let's say, skiing on the mountain, right? So it's very simple heat transfer basics here, 3 ways to transfer heat. It's really important to understand that so we can talk about how the heat is lost as well, right? So when we talk about material properties, the thermal conductivity is the U value, right? It's the inverse of the R value or thermal resistance. And basically thermal conductivity is it's rated per inch, and it's a basic part of defining how much heat can be transferred when it's in contact with, let's say, the wall, all right? Thermal conductance is just your conductivity times your thickness, right? So we talked about thermal conductivity. You multiply that by your thickness and you get thermal conductance. Of course, thermal resistance, everybody's probably familiar with R values. Resistance is just the inverse of the U value, 1 divided by the U value. Of course, your U value is 1 divided by the R value. So you can easily flip this back and forth, okay? So those are the 3 pieces here, and I'm going to show you how that fits into load calculations and why you actually need to look at insulation values and defining the entire wall, right? And how that impacts the load or ceiling or anything that's the outside of a building, right? The thermal envelope of a building. When we talk about R values, table A1-3 is what is R values listed. There's some generic values in Manual J, and obviously what they build into load calculation software. R values for the materials, if it's easy for heat to transfer through it, the R value will actually be low. If it's really hard for heat to go through that, the R value is really high, right? So it's rated per inch, all right? And it's the inverse of the U value, so 1 divided by the U value. So you can figure out what the R value of a window is if you know the U value of the window. You just divide it by 1 divided by the U value. That'll give you the R value. And what you're going to find is most windows are the weakest point in the wall, right? Unless you have some really great triple pane argon glass kind of windows. But most likely windows are the worst part of your wall when it comes to R value, because you could have R19 in a wall and R3, let's say, in a window, right? So keep in mind when you're doing this, though, especially in your software, particularly in your software, when you're doing a site survey, you're going to count the entire wall, just not the R value of the insulation in the wall. So if you have brick on the outside, the R value of brick is 0.44. It's not much, right? It's really easy for heat to actually go through brick, but it can actually hold some thermal mass. That's another story, not for today. The insulation within the wall, and then of course the drywall on the inside, which is what your vapor barrier typically is, right? Your R value on drywall is about 0.45. So when you add all of these up for this particular wall, we actually have a total resistance of the wall of 12.89. And that's why the software asks you what is on the exterior of the wall, if there's any foam board, if it's 6-inch studs or 4-inch studs, and if it's wood or it's metal, and then what the interior finish is, right? Because they're adding up all of these R values in the software for you. All right, so let's move along. If you don't know what the R value is supposed to be, because you are supposed to be looking at this on the site, obviously if you're one of my elite members, you probably walked through the site survey course that we have available on Patreon. It's the first, let's say, 7 to 10 videos in numbered numerical value. If you've been through that, you've probably seen this chart. This is a great chart from Oak Ridge National Laboratory, and this is basically what you see and you measure the depth, you'll know that per inch is the R value on the right-hand side, and you can figure out what the actual total R value is for the insulation, let's say in a wall or in a ceiling. So as an example here, if you have 6 inches of let's say loose fibers and they're gray, that's cellulose. It's 3.7 times 6 inches, gets you really close to our please forgive me, I don't have a thing here, maybe R21, right? So really important, you actually see it and you measure it, okay? If you have closed cell spray foam, that's actually 6.5 per inch. So that's not on the chart. Since Oak Ridge actually put out this insulation fact sheet, closed cell spray foam has become way more popular, let's say on a hut roof or something like that when you're building homes these days. So really important, you're defining the R value that you see, okay? Just because you have, let's say, R30 in a ceiling and you actually have 3.7 per inch, so 30 divided by 3.7 is actually 8 inches of cellulose. So let's say you go up in the ceiling and you see 8 inches of cellulose. That doesn't mean the entire ceiling is R30. You actually should take a weighted average. Think about this. The ceilings are 30, but then you're going to cut in a bunch of holes because you're going to put ductwork in the attic, and now you're connecting an R8 duct to meet code, and you're going to insulate that the four-way register or the boot, right? It's going to be insulated to R8. That is now the weakest part in the ceiling. Or you could have worse. You could have an uninsulated, let's say, pull-down stairs for your attic for access. So all of these things you need to take into account and actually get a weighted average for the insulation value for that ceiling. This is where a lot of people start to miss. And I'm going to show you how this starts to impact your load calculation. It can get pretty drastic if you have large ceilings. Let's say, a colonial style home with just one large ceiling across, or a ranch style house where it could be as much as 25% of your heat loss is your ceiling. So really important, you take into account all of the components, and this is what it's going to look like for you. So as an example, I have an attic ceiling and I saw that 8 inches of cellulose, that's R30, right? I have an access hatch and it's uninsulated. I have an R2 value for wood, all right? R17 for rafters, and then of course grills and registers are insulated to R8 where all of those holes are. And if I add up all of the area of that, so I have a 920 foot ceiling, and out of that 920 feet I deducted for the square footage of my grills and registers, the square footage of my rafters, and then of course the 4-foot access hatch, right? So that must be 2x2, really small. We're not going to be pulling stairs down on that one. All right. So you can see R value is 1 divided by R value is going to be your U value. So 30, right? 1 divided by 30 is 0.033. So that's where we come up with U value, and we move across. We have an area of 802, and then you multiply that out. Your U value times your area is 26.5, and for those that are very up on heat loss, you know that is the majority of the equation. If you know temperature difference, you can get heat loss, right? So really important here. You do all of the math to find out how much each R value is being weighted, okay? Of course, access hatch, it's R2. When you divide 1 divided by 2, it's only 0.5. You have a 4-foot square area, so 4 feet times 0.5 is only 2. So that is your UA, your U value times area. And you just do that for the rafters and the grills. And then you would add up all of those UA values all the way on the right-hand side in order to find out what your total UA is. And then you get your total area, 920 square feet, and you divide it by the 36.25 total UA to get what your actual weighted average R value is for that ceiling. So in this example, a really well insulated ceiling, your registers are insulated to R8. It's probably 2x8s up there in order to get that R17. You can see it's still R25. It actually comes down, and it's easier for heat to be transferred across that ceiling with all of these holes. It's like Swiss cheese, okay? So really important, you take a look at the whole ceiling and enter a weighted average R value, not just R30, because that's what the ceiling has, okay? All right, so let's move along because I want to explain what voids do. So if the insulation isn't installed correctly, and I used to see this a lot because maybe the weatherization company did air seal and insulate it correctly at one point, but then let's say the cable guy comes out, kicks a bunch of insulation aside, right, in order to run his cable upstairs in the attic, but he doesn't smooth it all back out and make it all nice and even, and now we have voids. So it's really easy that if you have 2% voids of air in that insulation, you can cut your R value in half, all right? So you can see it right here, R19 would drop down to R11.5. There's a huge drop. So as an example here, if I had 2% voids, or let's say that insulation was not professionally installed and a homeowner did, they just went down to Home Depot and rented the sprayer and just threw it in their attic. And it looks just all wavy through there. So in that instance, I have to kind of get an average of the height, and then I would say there's probably some voids because I didn't install it correctly. So I would actually derate my R value for the insulation. So if I threw that into the weighted value, average value of that sheet, right? So instead of R30, I had R15, which is quite possible if you don't have a professional install that insulation. All of the other stuff in the ceiling remaining the same, when I do this math, instead of an R25, I'm only working with an R14.5, right? Or worse, if you thought it was R30 and that's what you entered because you didn't even use the weighted average sheet, you can see how this is going to impact the heat loss of your ceiling, okay? And I got some math to show you exactly what it does in a minute here. So really important, seeing is believing. This is why when you type up, and I shouldn't say you, but when people type up and they don't believe load calculations, it's probably because you didn't put the right numbers in, or you didn't understand where the numbers come from or what the values need to be. Just when I picked up my phone and I use it as a calculator here, I can type in whatever number I want. If the number that doesn't come out and I don't believe it, that's not the calculator's fault. It's not the software's fault. It's not the processor's fault. It's my fault. I'm the one that put the numbers in, right? So really important you understand the process and you know what you're looking at. Seeing is believing, and that's how you're going to trust the numbers. You're going to trust the calculation, okay? All right, so let's move along. Let's talk real quickly about transmission coefficient. So this is U value, and U value is based on 1 BTU per square foot per hour. So you can see here, there's a 1 degree temperature difference across this square foot of block, or whatever you want to call it. And when there's 1 BTU per square foot per hour across it, it's a U value of 1. Very, very simple, okay? Obviously, just so you know, that's really, really bad. You want a really low U value, right? So really important to understand here. U value is the transmission coefficient, okay? So when you're looking at this, just like R value, you would add up all of the R values, and then you would divide 1 by your total R value in order to get the U value of that wall. So as an example here, we might have, outside surface as wood siding. You might have asphalt sheathing, R11 insulation, 1/2-inch wood studs, gypsum board on the inside. You add up all these R values, In this example, to get a 14.445. Obviously looks familiar from earlier. All right. We take 1, we divide it by your R total, and that gives you a U value for the whole wall. Okay. You got to be careful here too. Obviously there is some weighted stuff here, but we're going to add up the whole wall here in order to give you what's a really close number for the whole panel. All right. And then, of course, in order to make this math work when we get to heat loss, you need to know what your design temperatures are going to be. Obviously, this is going to be your indoor design conditions minus the outside design conditions based on tables 1A or 1B, not whatever you think it's going to be. So very, very important here. In this example, we want it 70 degrees inside. Just so you know, code is 68 to 72. 70 is right in the middle. And then, of course, your outdoor design conditions. Obviously, 0 here in the Northeast is a common number that's used. Doesn't mean it's correct. Sometimes it's 12, sometimes it's -5. Depends on where you're working. You should look that up in Manual J, version 8, tables 1A and 1B. All right? That would be your delta T across that wall, ceiling, floor, whatever it is to outside. All right? And then, of course, in order to get heat loss, what I'm going to show you is just the math for conduction. All right? This is not including infiltration. All right? So infiltration is the air movement through the house and how much is being lost with the air movement. Conduction is really simple math, and that's typically what we're talking about with heat loss through windows or walls or doors or ceilings or floors. All right? But it's conduction plus infiltration. And obviously, this is where a lot of people go wrong when you start estimating heat loss. And if you try to do the math longhand and you don't know about infiltration and you just forget about it, no wonders your heat loss is too low, or you're using a rule of thumb and your heat loss is too high because the new homes are a lot tighter than the old homes, okay? In order to meet code purposes. I won't get into that today. Just keep in mind, heat loss total is conduction plus infiltration. So we're going to talk about the conduction side and what the weighted R values actually do to your heat loss, all right? So let's take this example of I poked my head in the attic. I saw what I thought was R30, and that's what I entered for the ceiling. I didn't use the weighted average sheet. I didn't derate anything. I just did this simple math here. And of course, your heat loss is your U value times your area times your delta T. So in this example, R30, the U value is 1 divided by R30, right? So 1 divided by 30 is 0.033. We times that by the area of 920 square feet, and we times that by 70 degrees, delta T across the 70 degrees inside and 0 outside in my attic because it's vented. And we end up with 2,125 BTUs per hour for that ceiling, okay? It's actually not bad. That's pretty good. That's a well-insulated ceiling for a 920 square foot ceiling. That's probably small ranch, right? All right, let's take this a step further. Remember when I took that area weighted average and I brought it down, right? Because I took into account all the joists and the Swiss cheese I was cutting into the ceiling and the 2x2 access, right? And now instead of R30, I have R25. So 1 divided by 25 is 0.04 times the same square footage, 920 square feet, times 70 degree delta T. And guess what? Now we're up to 2,576. It doesn't sound like much, but we just added 21% heat loss to that ceiling, okay? So this little bit, particularly in a really low load home, starts to impact the heat loss in every single room when you do duct design or you're sizing ductless or whatever you're doing in order to serve the heating and cooling for those spaces. So really important, use the area weighted sheet, right? Now, what happens when we derate the R value because it wasn't installed correctly, right? We brought that down to R15 or R14.5 to be exact. 1 divided by 14.5 is 0.07 U value. 0.07 times 920 square foot ceiling times 70 degree delta T. We just jumped that heat loss up to 4,508. That's 112% more than what the original calculation was. And if that insulation isn't installed correctly and we just have 2% air voids in that insulation, we could easily miss what would be half the heat loss of that ceiling. And no wonders it's cold when it's 0 outside in those rooms. So really important you take the time. Seeing is believing. You have to look in the attic. You have to take a peek, let's say, with a non-conductive probe. I used to use one of the plastic knitting probes. Take an electrical outlet cover off, get my probe between the outlet and the inside of the wall to see what I have for insulation in there. See what the depth is, right? Seeing is believing, and that's how you're going to be able to trust the load calculation. All right, so in conclusion, we covered the basics, right? We talked about convection, conduction, and radiation. We talked about how that fills into material properties, what the properties of those materials are, and how we're going to transfer heat through them, and what the resistance value is, and what the conductance value is, the U value, 1 divided by the resistance value. The temperature difference across that wall, if you know these items, you can easily calculate the conductance heat loss. Don't forget about infiltration. This is why we don't do it longhand, right? And why we use software to bring that piece into it, what the air changes per hour are, or you better take a really good air-educated guess based on the size of the home and the age of the home as to how much air is going to be changing over in that space. So what did you think? Did you like the video on Manual J and how seeing is believing? If you did and you want videos like these 1 year in advance, head over to my Patreon page. The link is below, and you can join for as little as $8 a month. There's a whole ton of content on there, including modules on residential system design for my elite members. Thanks for joining me this week at HVAC Pro Blog, where we provide advice for residential system design, quality installation, and system diagnosis. I'll see you soon.